The remainder of chapter 1 covers two main ideas. The first one is inequalities, and the second one is absolute values. And there's also the crossover between absolute values and inequalities, which are absolute value inequalities. And I think these two topics in particular are kind of tricky for kind of unexpected ways. I think uh, I think inequalities, people kind of assume that they're really simple, and then there's actually some more complexity to them sometimes when you get more difficult ones. And then I think absolute values, students tend to think that that's a really scary thing that's hard to deal with, when in reality it's not. So they're kind of not exactly what you would expect there. So anyway, starting off with inequalities and the basics of inequalities. Inequality is just a mathematical statement that states the relationship between one thing and another. Uh, just like an equal sign. But in this case, we have a different relationship between the two statements. So, or the two sides of the statement. So, these are the symbols that you're used to seeing when you talk about inequalities, right? It's greater than, less than, greater than or equal to, less than or equal to. One of the things that if you're a high school student and you're hearing the word inequalities in a math class, you're probably like, oh, I remember that my middle school teacher said if you divide or multiply both sides of an inequality by a negative number, you have to flip the sign. And I don't know that that's always thoroughly explained, so I wanted to do that now. It comes down to something called the law of trichotomy, where if you have two values, A and B, the only thing that can be true is that they're equal to each other, greater than each other, one's greater than the other one, or one's less than the other one. You can't have two of those things be true at once. It doesn't make sense. And so if that's the case, when you have two numbers, like for example here in 4 and is greater than 3, that's fine. Okay, obviously 4 is greater than 3 if we think about it left to right on a number line. But if you divide both sides by a negative number, is that relationship still true? So, is -4 greater than -3? No, it's not. In order to maintain this true relationship here, we'd have to flip this sign to make it a less than sign. -4 is less than -3. So it's all really just as long as you remember to do the flip the sign when you divide or multiply by a negative number in the process of solving, everything will be fine. Something that may or may not be new to you here is called interval notation. Interval notation is kind of the preferred and more modern way to represent the solution to an inequality. So whereas you're used to saying something like x is greater than 0, what interval notation, x is greater than some value a, what interval notation says is that x is anything that is a, not including a, all the way to infinity. So these open parentheses here, these parentheses mean it's like open. So you might be thinking like an open circle right there on the number line. You might be used to seeing something like that. That would be written in interval notation, parentheses a, comma, infinity, parentheses. Okay, x is greater than or equal to a. Now we have a difference. We have this hard bracket. We're used to seeing that as a solid line, right? So solid line and on. And then if you had a different value, so if you're going the other way again, not inclusive. Parentheses in interval notation are non-inclusive. Brackets are inclusive. And we'll get some practice on how to use interval notation in later on in this video. But it's what we'll be using for this class. Uh, Anyway, we just talked about this. Now, one thing that's really important to keep in mind is that infinity, when used in interval notation, should always, always, always have a parenthesis around it and never a bracket. And the reason for that, of course, is because that was bad infinity drawing. Hold on, sorry. Is because infinity cannot be contained, bro. You can't contain me, bro. You can't contain me, bro. Never put a hard bracket around infinity. That's saying that it can include infinity. Nothing can ever include infinity. It's not even a number, right? It's just it's like the limit, essentially. Okay. Um, it's all there's a directly related, like a parentheses are open circles and filled in circles are brackets. For purposes of my class, when you're graphing it, I don't really care if you stick to your open circles and closed circles or your parentheses and your or your brackets. Either way is fine, as long as at the end when you write the solution in interval notation, you're using interval notation correctly. So let's just solve this inequality here, which is not necessarily a super simple one, and then write the solution in interval notation. I was going to graph, okay? So first step, we're going to multiply both sides by 3. This is the multiplication property of inequality. Okay, so that's going to give us negative 7x plus 4 on the left is greater than 18. Subtract 4 both sides. That is the subtraction property of inequality. Negative 7x is greater than, what is this? 14. Okay, now we're going to divide both sides by negative 7. And in doing so, we have just flipped the relationship here. So we're going to have to flip the sign. I'm going to write down our next step. X is less than negative 2. So I need to graph x is less than negative 2 on this number line. So I'm just going to put negative 2. Some teachers will have you put 0 on it somewhere, but it's okay, negative 2. And now I'm going to have an open circle at negative 2, and if x is less than negative 2, it means I'm going to shade to the left. Okay, so that's the graph. Now, you could have had, I'll just write a few of these things above, you could have put a parentheses like that at negative 2, like that. And you could also write your answer to your graph of your number line kind of above the number line. Teachers teach all kinds of different methods for doing this, and to be honest, it doesn't matter how you do it, as long as at the end you're writing your solution in interval notation correctly. And how we do that is we read from left to right. So looking from left to right on this number line, okay, it goes all the way to negative infinity over here. So we're going to write negative infinity, and you cannot contain negative infinity, so it's non-inclusive. And then we're going to put a comma, and we go all the way to our next situation, which is a non-inclusion at negative 2. So we're going to put negative 2, not included. There's nothing else over here, so our answer is simply this. Okay, so the combination of the graph and that solution that's been boxed is your answer to this. Okay, now unfortunately, that's fairly simple, but it gets more complicated than that. And before we move on to the more complicated part, let's just kind of review how this interval notation works. So, I didn't put numbers here. Oops. Let's just put random numbers. So negative 3, 4. Let's put a negative 2, negative 1, and let's say like this is 6. Okay, if these numbers are here, let's write these in interval notation. Okay, we have an open parentheses and open parentheses. So it's going to be negative 3 to 4. Those are open circles, are non-inclusive. This one, we read left to right. It's non-inclusive at negative 2. It is inclusive at 1. So hard bracket for inclusion. 6 is included, and it goes all the way to infinity, non-inclusive. So it's just read left to right. Okay, there will never be a case where you have anything in between the two numbers like this. It should always just be a comma. Okay, there should never be like another symbol, and we'll show you what those symbols might be in a second. So compound inequalities, it kicks up the difficulty a little bit. We end up with two different kinds of compound inequalities: conjunctions, which are and statements, and disjunctions, which are or statements. Conjunctions are true only when both statements are true, and disjunctions are true when at least one of the statements is true. So this example here, negative 1 is less than x is less than 3. You could think of this as two separate inequalities where x is greater than negative 1 and x is less than 3. And then you would shade where both of these things are true. In practice, this is maybe a little bit more difficult. So there's kind of some stuff to help us, but let's just tackle one compound inequality right now to see how we might go about doing these. So there's kind of two ways to do this. You can, and I'll show both real quick here. So you can think of this as like an inequality with three sides, sort of. You have a left side, a middle side, which is not a side, and a right side. And what you do to one side, you have to do to both the other sides, sort of, okay? This might be confusing to you, so if it is, hold on, we'll get a kind of a more clear method of doing this. For me, I'm trying to isolate the x, right? So I'm going to get 2 away from, out of the denominator there by multiplying all the sides by 2. And so that sounds a little weird, okay? 2 times negative 2 is negative 4. Is less than 3x plus 2 is less than 14, 7 times 2. Okay, now I want that 2 out of there, so I'm going to subtract 2 from all sides. Okay, So now I'm going to have negative 6 is less than 3x is less than 12. And now I want x by itself, so I'll divide all sides by 3. And I've got negative 2 is less than x is less than 4. Okay. And we'll graph that in a second. So we're going to come back to this. The other way of doing this is to look at your two different inequalities to start with. So the relationship from the middle part to negative 2 and the relationship from the middle part to 7. And solve them both individually, and then you'll have two inequalities to graph. And we'll just show that real quick. And it's up to you however you want to do these kinds of inequalities, because it doesn't matter. You'll get the same answer either way. I think the option we showed first is faster usually, but sometimes it's less confusing to do this other way. So let's write the two inequalities then. First, we would have negative 2 is less than 3x plus 2 divided by 2, and we would have, let's do this one over here, I guess. We'd have 3x plus 2 divided by 2 is less than 7. So solving these in is very similar, 2 and 2. So we have negative 4 is less than 3x plus 2. Subtract 2 both sides. Negative 6 is less than 3x. And at the end, you'd have x is greater than negative 2. Okay, I just kind of rearranged that. All right, this one, we're going to multiply again, both sides by 2. And we'll have 3x plus 2 is less than 14. Subtract 2 from both sides. 3x is less than 12. Divide both sides by 3. X will be less than 4. So here's what I have, right? I have this compound inequality written like this, and I have these two separate inequalities. These taken together, these two taken together are the same as this one written by itself. And there's kind of strategies for doing this. One way that people like to do is to say, all right, if I have x is greater than 2, let's say here's negative 2 and here's 4. I kind of start above the number line and I say if x is greater than negative 2, well, that would look like an open circle, and we're shading to the right because x is greater than. And then x is less than 4, that would look like an open circle because less than and not equal to. And we shade to the left. Ah, man, sorry, my hand got stuck there. We shade to the left. And then the solution to this compound inequality, this particular one, which is a conjunction, it's an and statement. We shade where they're both true. So we'd have open circles on the negative 2 and the negative 4 and shade in between. And then in interval notation, we would write negative 2, comma 4. And that's our answer. And so that's correct. Now, all of this is sort of confusing. How do you know they're going to overlap or not? Like, how do you know it's an and statement and an or statement? Before we talk about that, we got to talk about how you accommodate for these things, or a special notation when it comes to interval notation, a special symbol that we use a lot, some more than others. And so this is kind of important here. Okay, we have these two symbols that are in red here. We have this upside down U, which is called the intersection symbol, and we have this like right side up U, which is called the union symbol. Now, in the process of us writing out the solution to an inequality, you're almost never gonna see the intersection symbol as the solution to an inequality. You might be given a statement that has the intersection symbol in it, and like be asked to like write what is the solution to this. It's more likely to be part of a question, whereas the union symbol is going to come up often when you have to express multiple regions that have been shaded on the number line in the same statement, sort of. And we'll see an example of that here in a minute. So intersections are related to conjunctions, and unions are related to disjunctions. And again, you almost never, in fact, I would say in this class, you will never write the intersection symbol as part of an answer to an inequality question. Okay, so and the last thing, sorry, is these tend to get overused. I've seen students just put union symbols in their statements when they think it's supposed to be there, and they just are not sure. If you're not sure, right, then you probably, first of all, don't know what you're doing. But if you're not sure, don't put it, right? I mean, if you're gonna miss that, you're gonna miss it. Don't put too many of it. Then your answer that you provide is just gonna be completely weird and make no sense at all. All right, so let's jump into an example after we talk about how you know the difference between a conjunction or a disjunction. So if I gave a problem like this and it said graph the solution set for -1 is greater than x is greater than 2 and express it in interval notation, how do you know if these are going to be like a union, if you're going to use a union symbol here or not? Well, you could solve the problem all the way out, or you could do this thing called the Calluson Convention and know what to expect going into it. And this is going to sound super stupid, and part of that is because it is, but this is it, okay? If you read the statement out, like for example, down below here, we have -1 is less than x is less than 3. Less than x, less than 3. If it's less than, it's and, than, and. So than and kind of rhyme a little bit. That means it's a and statements are conjunctions. This is going to be the answer to this is going to be something like, well, it's going to be this. Okay, this is going to be the answer. You wouldn't know that without experiencing, had enough experience, but that's going to be the answer to that one. Notice how there's no union symbol whatsoever. Okay, the next one says -1, I'm reading over here, I'm reading from like left to right. -1 is greater than x is greater than 3. Now it said or, right? Or greater than or statement, right? Disjunction. Now the thing about this that's really stupid is that, of course, greater than also has the than that we said was an and before. Just anyway, you just got to buy in here, okay? So greater than is an or statement. This is going to end up actually being a disjunction, where it would look, the answer is going to be this. Now you don't know exactly how to get to this answer from that statement right away, so there's a whole procedure for this where you put it on a number line and then kind of write down what it says. But we're going to run into an example here in just a second where we actually end up with a disjunction, okay? And that'll be the last example that we do in this video. Actually, sorry, not. We're gonna have these ones here. So let's look at this. -2 is greater than x is greater than 3. This is a disjunction. I expect to use the union symbol here. But if you're unclear about how to go from point A to point B, look at this. Look at these statements individually. Okay, we have -2 is greater than x, or if we want to switch this around, right? X is less than -2. Okay, same thing. If we look at this statement right here, this is x is greater than 3. So put these above the number line, kind of, right? So let's say if we put -2, well, let me put these in black. If we put -2 and 3 on the number line, well, x is less than -2 would look like this, okay? And x is greater than 3 would look like this. So there's no overlapping here, so I'm just going to transfer this down right to the number line, and I'm going to do a little thing here. Instead of these open circles, I'm going to have a parenthesis. Same thing, okay? A parenthesis like kind of opening in that direction that I'm going to draw my arrow. So over this way and over this way. And how do I write this in interval notation? Well, all the way over here is -infinity, right? And it can't include -infinity, so -infinity, comma, -2. And now how do I say it's this and also this stuff over here, this or statement? It's either, you know, x is less than -2 or x is greater than 3. It's this union symbol. You draw this U right here. So it's kind of how you accommodate a gap in the number line when you still have more information to write later on. Okay, so then 3 all the way to, of course, positive infinities over here. And that's it. All right, now this next one. -5 is less than or equal to x is less than 3. Less than and. So this is a conjunction. And again, we can write this out as two separate things if that is how you prefer to think of it. This would be like x is greater than or equal to -5, and this part would be x is less than 3. So do the same thing where we have -5 on the number line and 3. If we start above the number line, okay, -5, right, and it's greater than or equal to. So it's actually a solid dot, and my bad, shade to the right. And then 3, it's an open circle, and we shade to the left because it's less than 3. So the solution to this is where they overlap. It's an and statement where they're both true. So we have a solid 9 here, or let me undo that. We could put it as a hard bracket, okay, instead. And then a open parentheses there, and we shade in between. And then how do we say the answer? Well, it's just -5 to 3. That's it. Okay, now let's look at a real world example here. Not real world, but just an example. And it involves our worst nightmare, an absolute value and an inequality in the same sentence. Okay, an absolute value inequality is nothing more than just a compound inequality. Just a quick review about absolute values, and this will be a subject of the next video. But if you had the absolute value of something is equal to 1, this is an equality, there's two things that could be true here. It could be exactly what it says it is inside there, or it could be the exact opposite of what it, the exact opposite of what it says it is equal to that. Now, if you divide both sides by -1 here, you get x is equal to -1, which is why you would normally see this written as x is equal to plus or minus 1. Okay, so just keep that in mind here in a second, and we'll kind of transfer that over to this inequality. So it could be exactly what it says it is. X plus 3 could be greater than 5, or x plus 3 could be greater than 5. The opposite, right? This is the exact opposite of x plus 3. Now at this point, if we divide both sides by -1, we have x plus 3 is, and then we have to flip the sign because we just divided both sides by -1, is less than -5. So oftentimes what you'll see and teachers will tell you to do is when you're given this inequality, just straight away write it like this. So you can write it, x plus 3 is actually without the inequality sign, so you just write x plus 3 is greater than 5, and then on the other side, kind of keep this, if that's a greater than, then this should be a greater than, and make it the opposite of what's over here, so -5. Notice how that is exactly what we have. We have this one and this one that we're going to solve independently in graph, but that's the same as this compound inequality here. So if you can go, if you kind of understand that, you can go straight from this absolute value inequality to that compound inequality because they're the exact same thing. Or you can write it as these two separate statements, but it's important to kind of know why this is true, and we get that from looking at the idea behind an absolute value. So I'm just going to go ahead, since we already came up with this compound inequality statement by itself, let's just solve this using that method where we have kind of 3 sides. So subtract 3, subtract 3, subtract 3. We have -8 is greater than x is greater than 2. So -8 is greater than x is greater than 2. This is going to be a disjunction. So we're going to have, we are going to have -8 and 2 on the number line. And if I graph, let's see, if I graph this part, right, that's going to be a a closed circle, and we're going to shade to the left, right? That's what x is less than -8. And then this part, x is greater than 2, would be like this. And so we're just going to put that down on the number line now. Well, actually, let's do it with the with the brackets, with the parentheses for non-inclusive. Okay, and then we'll just put this in. So it's -infinity to -8, and then union to represent this space in between, because it's an or statement, 2 to infinity, and then we're done. Okay, so this kind of, and this is a long video, but it's really, if you're comfortable with interval notation, you can handle any of these much more difficult kind of inequalities that we're going to be talking about in the next video, even the ones that have absolute value all over the place and denominators and all kinds of yucky stuff. So just watch those next, and then if you have questions, of course, ask them.